at statistics. Before we start looking at statistics, let me add Michael to class. And my math lab homework 14 will be the first homework from statistics. That'll be due on Tuesday the 3rd. Project 2 is also due on Tuesday the 3rd. How is that? Has anybody started looking at their project? Does anybody have questions on the project? Connor, are you asking something or no?
Nope.
Okay.
Professor?
Yeah.
I have questions. I had to leave the other day. I work on Tuesdays and Thursdays now, and I have to be there at 9:30, so I have to jump right out at 9:15. So I left and I didn't get a chance to hear you go over the project. If I read the directions and everything, well, should I be fine?
If you're not, send me an email and I'll walk you through them again. I can make an appointment with you and go over it with you in Zoom.
Okay.
Okay.
And it's in Blackboard, the project information?
It's in Blackboard, in the folder for projects. There's two things for project 2. One is I think it's either a PDF or a Word file with the project directions, and the second is a Dropbox for you to put it in. And I don't think I said so last time, but that stuff, if you're not using a spreadsheet, that stuff can be a pain in the ass to type. So don't worry about it being handwritten. Just try to make it legible if you do give me a handwritten project. Okay. If there are no other questions, then today we're going to start looking at statistics. And I am guessing that probably absolutely every one of you has heard of statistics. What is it? All heard of statistics? Yes?
Yes.
We're going to look at statistics as being a study of data. We're going to see that under that general heading of statistics, there's going to be a lot of things. Statistics involves collecting, organizing, summarizing, presenting, analyzing, interpreting, data, and using data to make predictions. We break statistics into 2 parts. We talk about descriptive statistics and inferential statistics. In this class, we'll spend probably more time on descriptive statistics than on inferential statistics, but we'll look a little bit at some inferential and using statistics to make predictions, to draw conclusions. If you take the statistics class, Math 164, you'll find that what we do in here is only the tip of the iceberg. What we do in this quarter of a semester, we give you good foundations to start if you're taking a statistics class, but it goes ever so much further in that idea of inferential statistics. The descriptive statistics involves the collection, the organization, the summarizing, and the presenting of the data. It's gathering the data and putting it all together and trying to make it look nice, make it have some sort of meaning. Inferential statistics is when we generalize and use the data to draw conclusions. And I think being that this is an election year, we see an awful lot of data and statistics thrown about with respect to the election, with everything that's going on with the pandemic. We see an awful lot of statistics being used. We're going to look at how some of that is done. When we talk about statistics, we differentiate between a population and a population is the set of everything that's being considered. And so an example might be if I wanted to do a study on something involving college students. Let's say I wanted to see how did your campus's response to the pandemic affect you? And so something like that, my population could be something like all American college students. And so if I wanted to do a study where I wanted to ask all of the American college students in this country what they feel about their campus's response to the pandemic. Think about all of the college students in the country. Would it be feasible? Would it be possible? Would it at all be achievable for me to get data to ask questions of every college student in the country? Could it be done? Could one individual do that? What do you think?
Ask every single college student?
In the country, yes.
No.
No, it's not possible. And an awful lot of times the population is overwhelming and unyielding. Another example of a population that you see them trying to get to regularly, if you look at any type of media, you might have a population of all American registered voters. And when they try to say something or another about the electorate, either the population that they're dealing with is everybody registered to vote. Do you think it's feasible for whatever media venue is making these claims to have reached every single voter in this country, every person, not even voters, but every person registered to vote in this country?
No.
No. And so what happens is, because populations are often difficult, unwieldy, too large, we use a sample. And a sample is any subset of the population. But we're going to see that some samples are easy to get, but not necessarily the best. And we're going to try to kind of come up with a way of describing what would make a sample good. So if I first look at that population of all American college students, would an example of a sample would be students in this class. And for that matter, if I look at the population of all Americans registered to vote, are most of you folks registered to vote?
Yeah, I'm waiting until Tuesday.
You're waiting until Tuesday
Yes.
to vote, but you registered, yeah? And so couldn't we use as a sample, again, the students in this class?
Yeah,
They're both subsets of the population, but are they good subsets? Are either of those representative of the population? Do you think the experiences of people in this class would represent the experiences of all of American voters? Do you think the experiences in this class would represent the experiences of all American college students?
no.
No, they're not real representative. Because if you look at it, the students in this class are all at community colleges. We don't have the representation of four-year schools or universities. You probably all have similar majors. Most of you are probably all from a similar region. And a good sample should be representative of the population. A good sample is frequently looked at also as being a random sample. And in a random sample, each member of the population has an equal chance of being selected. So for a better representative, a better sample of all American college students, what I might do is I might, for each state, put the names of all the community colleges in a hat and pull out two, and maybe all the four-year colleges in a hat and pull out two, maybe all the universities in a hat and pull out two. And then from each of those colleges, put all the students' names in a hat, and from each campus maybe pull out like 100 students, and it would be random, and it would be representative of all of the regions of the country and all of the different types of campuses in the country. When we look at this idea of sampling, there are some classic bad sampling techniques. And one that you see used a lot is convenience. So what would be a convenient sample? The people in front of me. And just because that's the most convenient sample doesn't make it at all representative. Another bad technique is if it's self-selected. Sampling. And what do I mean by that? Self-selected sampling sampling part of me is like when you choose to respond. An example of a couple of examples of self-selected sampling. One, do any of you ever get in the mail at all those great big glossy flyers from your local politicians saying, I care what you think? On the back of the flyer, there's a little survey and they ask, what do you think about, let's say gun control or abortion or health care, and they want you to mail it back.
Yeah,
And when you get those and they ask you to mail them back, do you really think they're interested in what you're thinking, or do you think they really just want you to see their face? How many of you actually send those back?
I throw them out.
Do you think most voters throw them out? Do you think most voters put them in that circular file? Yeah.
I
Who
think the
mails
ones
them back?
there.
Who mails them back? Who responds to those?
The secretaries, the ones that.
Okay. Yeah, but in terms of like the people who get that flyer at home, the people who take the time to answer the questions and put them back in the mail, wouldn't those be more like the people with extreme values, the people who feel very strongly on one side of the issue or the other? And it doesn't, the responses that they get wouldn't represent the entire group. It only represent the extreme views of people who have enough time to respond and take enough time to respond.
My grandfather does that.
Yeah. Is he got strong opinions one way or the other on most things?
Yeah, he's very big with politics.
Yeah. And aren't the only people who respond those people who are like that, which I don't think is the average person in the district. Another one that drives my husband crazy, not so much since the pandemic, but last year one of the local news stations used to put out a question every week, and which is the best pizzeria in Western New York, which is the best hamburger joint in Western New York. And it always seemed that the winners were some of the most obscure places. I think that won best pizza in Western New York was this random bowling alley in Springville or something like that. Do you really think that random bowling alley in Springville has the best food in Western New York? Or do you think that random bowling alley in Springville gave the most prizes to customers who called in with their name, something like that? And so again, that idea that people who choose to respond, like to call into a survey on the news or text in or respond to an email survey, that they're not necessarily representative. The people who choose to participate are going to be strongly one way or the other, and it doesn't give you a good representation. This idea of bad sampling techniques is something that's happened classically. We're not going to spend a heck of a lot of time talking about sampling, but I'd like to show you one example that I find really, really interesting. And then I want to show you the type of questions you're going to have to answer on this subject matter. So first, this is something that I pulled out of the virtual textbook on page 737. And I'm mostly concerned with this little article on the side. It says, in 1936, the Literary Digest, which was a magazine, mailed out over 10 million ballots to voters throughout the country. The results poured in, and the magazine predicted a landslide victory for Republican Alf Landon over Democrat Franklin Roosevelt. So they published that Alf Landon was the winner. Does anybody remember a President Alf Landon? Does anybody remember a President Franklin Roosevelt?
Yeah, he's my favorite.
Yeah. And so do you see, it was wrong. Why was their results wrong? They had 10 million people. That's got to be a large enough sample. Well, a whole bunch of things went wrong. in 1936, it was the Depression. Do you think they picked from their subscribers people who owned cars and things, people in telephone books? Think about 1936 as being during the Depression, the average person couldn't afford a magazine article or a car or a phone. And so they were only sampling from a small fraction of the society and not at all the average American. And so that idea of sampling the wrong people gives you very skewed results. I think we saw some of that with the last election 4 years ago when everybody was surprised with the results. 8 years before that, I know that my son was working on one of the political campaigns. And I don't know if you folks can think back to the first time Obama ran for office against McCain. And up until the night before the election, they had no idea who was going to win. They thought it would be so close, so close, so close. And it wasn't close at all. Obama won by a landslide. And I was talking to my son about it. And he said he knew that was going to happen because the polling technique was wrong. He said that so many of the polls that showed it being so close were telephone polls. But at that point in time, they were only using landline phones. Even 12 years ago, so most people didn't have a landline phone. The only people with landline phones were like older folks. Most people used a cell phone. Most people, under 40 didn't have a landline phone. So they were, again, only focusing on like an older population when they came out with those results that the two would be close. So again, I think this is a good example of how important that idea of sampling and picking the right sample be. Next thing I want to look at, the next page that I have in here, and I have no idea why, but lately this stylus does not want to work for me. So I'd like to look at some of the questions, a question or two, like how you're going to be asked these. I think I told you previously the questions in my labs correspond to textbook questions. So I pulled one out of the textbook. This says the government of a large city needs to determine whether city's residents will support the construction of a new jail. The government decides to conduct a survey of a sample of city's residents. Which one of the following procedures would be most appropriate for obtaining a sample of the city's residents? So let's look at each of them. If they were to survey a random sample of just the employees and inmates at the old jail, do you think that would be representative of everybody in the city and their views about it, or do you think that would be biased? Anybody have an idea?
Yeah, that would be biased.
It would be very biased, right? What about if they surveyed every fifth person who walked into City Hall on a given day?
Still biased.
It's still biased, not that many. Do you guys walk into City Hall very often? No, the only people who walk into City Hall are people who have city business. And so they would be more involved with the issue than the average person. How about if they surveyed a random sample of people within each geographic region of the city? If they took the city and divided it up to, like, let's say 4 corners and selected a random number of people from each corner, do you think that would work?
I mean, I would choose this one.
I think this is probably the best one that we've got here. The last one says the first 200 people in a telephone directory. Well, telephone directory would have, I guess, only people with landline phones. But if you think about the first 200 people, that would probably be an easy way of getting 200 people. But the first ones, wouldn't they kind of all sort of have the same last names just about? They're probably relatives or something, so that one's not real good either. And so can everybody identify, looking at a question like this, what's a good technique and what's the bad technique? again, people have gone on and got master's degrees and doctorates in this idea of sampling. And we're talking about it for what, about 20 minutes today. But can everybody sort of wrap their minds around the concept?
Yeah.
If so, we're going to go on then to the next thing. Once that data is collected, the idea of organizing data. And in order to organize data, I'm going to need to have some data. So for our first data set, I'd like to look at the shoe sizes of people in class today. And I have to apologize, it's a little bit cumbersome collecting this data. Usually if we were in a classroom, I kind of just go up and down the aisles and ask folks. But I'm gonna write these numbers down as you folks give them to me. So I want it as a whole number. If you're one of those people who wears a half size, please round it. Pretend you're ordering shoes online from a site that only gives sells whole sizes, not half sizes. I'll start. I wear a size 5. Debbie, what size shoe do you wear?
A size 9.
Janae, what size shoe do you wear? Janae? Janae?
Sorry, I'm a 9 too.
Okay. Robert?
9.
Sean?
We're a 10.
David?
Wait, what size was that?
10.
10. Sorry.
David?
Or 12s.
12. Gina?
I wear a 7.
Lucas? Lucas, are you there?
Yeah, a 9. I just have
9.
to check. I wasn't sure.
Okay. Chris?
8.
8. Ali?
I wear a 10.
Zach? B?
10.
Jackson?
12.
Michaela?
I wear a size 7.
Madeline?
A 9.
Colton?
13.
Connor?
12.
And Michael?
I wear a size 14.
Jesus, Michael.
Hey, I chose this as a data set because I thought it was I hope nobody's too self-conscious about something like shoe sizes. So here is the list. And as we look at that list of numbers, it's interesting, but right now it's kind of just all over the place. When we want to try to organize it and make it a more manageable list. The first way we're going to do that is by making a frequency distribution. When I say frequency distribution, doesn't that sound elegant? Doesn't that sound fancy? It really is not that difficult to come up with. For frequency distribution, what it is, it's a table that lists the data values and their frequency. It can include a tally. But doesn't need to, but doesn't have to. With any of these, it's important that you label everything. When we make these ways of organizing our data, we're doing it so that the person who's looking at our results can better understand it. And so we need to have everything labeled. We need to put a title on it. So I'm going to call my frequency distribution the shoe sizes of people in class. My data is going to be the shoe size. Let's go through and make a tally. Again, this one doesn't have to be there, but sometimes it makes your life easier in collating your data if you make a tally. And then let's record the frequency. And I'm going to shrink this down for a minute so I can still keep the list of numbers and make my table. I promise I'll make it bigger again in a minute. So our sizes run from 5 to 14. 6, 7, 8, 9, 10, 11, 12, 13, 14. And so there's a 5, so I'll put a slash mark there. Then there's 3 9s, then a 10, then a 12, then a 7, another 9, an 8. Oops, sorry about that. 2 10s, another 12, another 7, another 9, a 13, another 12, and a 14. And has everybody seen that idea of making a tally with the slash marks to help us count up? And so now my frequency is going to be how many slash marks I have, what my tally is. So there was 1 5, no 6s, 2 7s, no 8s, 5 9s, 3 10s, no 11s, 3 12s, 1 13, and 1 14.
Miss Trilla, there was 1 8.
Was there an 8? How did I miss that?
I think there's an 8.
Yeah, there was. How did I miss that?
Yeah, it's my size.
Yeah, I'm sorry. I apologize. That's what happens when I don't wear my glasses, right? Oh boy. And so does this table, is it easier to read? Is it easier to make sense of the data from the table than it is from the random list of numbers?
Yes.
Yes. Is it difficult to make?
No.
No, but it helps a lot with organizing the data. And that's called a frequency distribution. This is a general frequency distribution where each data value is separate. There's another type of frequency distribution that we look at, and that's called a grouped frequency distribution.
What is the one that we just did with the charts called?
It's just a frequency distribution.
Okay.
And this is a special type of frequency distribution where it's grouped, where we put the data in classes that are usually equal in width. And so normally in a normal semester, I would use the grades from exam 2 for this. However, because I don't have them all graded, I was trying to think of some other data I could collect from you folks for the grouped frequency distribution. And I thought I could use the date of your birthday. In whatever month. And so I'm going to try to make a list of those. So again, I'm going to go back and look at you folks. And I guess I'll start my birthdays in the spring, but my birthday, the date of it would be the 13th of the month. Debbie, when's your birthday? What day of the month?
The 16th?
Janae?
No, April 16th.
Janae, what's the date of your birthday?
July 20th.
The 20th. Robert?
The 15th.
15th. Sean?
7th.
David?
The 4th.
Gina?
I am also the 13th.
Cool. Lucas?
Yes, sorry.
What date is your birthday?
17th.
Okay. Michaela?
Mine's the 29th.
Chris?
Oh, my birthday's tomorrow, the 28th.
The 28th. Happy birthday, a day
Happy
early.
birthday.
Thank you.
You're so glad we had this conversation, aren't you?
Yeah.
I was kind of like, oh, she's gonna ask me my birthday.
Ali, how about you? Ali? Oh, well, Zach?
21st.
Jackson?
The 16th.
16th. Oops, gotta move this over. Madeline?
The 6th.
Colton?
31st.
Connor? Connor? Michael?
The 21st.
21st. Okay. So now I'm going to go back to sharing my screen. And I'm going to go through and make this larger. And so as I look at those numbers, they're kind of a lot more spread out. And so I probably don't want to include every number from 4 to 31. And so I might want to put the data in groups or classes. And so my first column, instead of having individual values, is going to have classes. And so let's say we're looking at the date of her birthday. And let's say maybe I want to break them up into groups of 5. So I might go, the 1st to the 5th, then I might go the 5th to the 10th to the 15th. But I'm going to stop for a minute and ask you guys, does that look right?
No.
Wrong with what I just wrote?
You'd be counting people with birthdays on the 5th twice, because they would go in the first column and the second column.
Does everybody see that we've got overlap here? So one thing that's important with the classes is the classes should have no overlap. There should be no shared values. No number should be able to go into more than one class. So again, instead for my dates, I might have 1 through 5, then I'll have 6 through 10, then I'll have 11 through 20, 21 through 25, 26 through 30, and then 31 through, I guess it would be 31 through 35. Although you really don't get past the 31st. So this might be an example where the one class might not be as wide as the others, and it might just be standalone 31st. And so now let's go and let's count up our frequency. And so let's see how many people birthday is 1st through 5th. And I'm counting 1. 6th through 10th, that would be 1, 2. Oh Lord. Why did you guys not yell at me?
What?
Shouldn't I have had instead 11 through 20, 11 through 15, 16 to 20, 21 through 25, 26 through 30.
Killing me, Smalls.
I know.
Yeah, sorry about that. I have no idea what went on there. So 11 through 15, let's see, that would be 13, 2, 3. 16 through 20 would be 1, 2, 3, 4. 21 through 25, it would be 1, 2. 26 through 30 would be 1, 2, and then above 30, there would be 1. And so does this make sense when your data is more spread out, that you might want to put it together in groups?
Yes.
When we have data in groups, we talk about class limits. We talk about a lower limit. The lower limits are the smallest value in each class. And so in our table above, the lower limits would be the 1, 6, 11, 16, 21, 26, and 31. We talk about the upper limits. And it doesn't make sense, the upper limits would be the largest in each class. And so from our table, our upper limits would be 5, 10, 15, 20, 25, 30, and I guess I'll put that 35 back in there. Then we talk about the class width. And the class width is defined as the difference between two successive lower limits or two successive upper limits. So for example, with this table, if I wanted the class width, I'm going to look at, let's say, the first two lower limits. The class width would be 6 minus 1 or 5. Or I could use two successive upper limits, which would be the upper limits of those classes would be 10 minus 5, which would also be 5. And so when I look for the class width, I don't subtract sideways. The class width is not 4. I subtract this way, 6 minus 1, so that my class width is 5.
I'm confused. I'm sorry.
Okay, class width. I'm not gonna, I'm saying how wide is each class? How many potential values are in each class? And in order to get that, I'm not gonna take 1 minus 5. Instead, I'm gonna look for two limits in order, 6 minus 1. I could have gone 26 minus 21. I'm just taking two classes in order. I can subtract lower minus lower, or if I wanted to, I could subtract upper minus upper. So the class width, it doesn't matter which classes you use. You can take any two classes. The class width here could be 26 minus 21, which is 5, which tells me I've got 5 values in each class. Or if I wanted to, I could subtract the larger limits, 30 minus 25. It also give me a 5. But if I'm using lower limits, they should both be lower limits. If I'm using upper limits, they should both be upper limits. And they should be from two classes that come right after each other.
So it doesn't really matter which one you pick to
It
get.
doesn't matter if you use upper or lower. But whatever you use, you have to be consistent. And they have to be from classes that come one right after the other.
Okay.
Okay?
Uh-huh.
And so that's a frequency distribution. And when I look at that grouped frequency distribution, it gives me a good idea as to where birthdays lie. But all of a sudden, I've lost each value, haven't I? I know how many people had birthdays in the teens, but I don't know what those dates were, right? And so that gets us to another type of way of organizing data. And the next one we're going to look at is called a stem and leaf diagram. And we'll use a stem and leaf diagram to organize 2-digit data values. When we use the stem and leaf diagram to organize 2-digit data values, the first digit, which is the digit to the left, is the stem. The second digit, which is the digit to the right, is the leaves. We make a column with the stems. We put the leaves off to the right. We want to make sure that the leaves are in order. Technically, you're not supposed to put a comma in between. When I talked to Mr. Krupa and Mrs. Jowsey that teach the statistics class, they're adamant. You're not supposed to put a comma in between. But that being said, in my math lab, they ask you to put a comma in between.
Why would they do that?
I have absolutely no idea, other than just trying to make it easier for the whatever algorithm they use to grade the questions to different.
Oh, okay, that makes sense, I
It's
guess.
a list of different numbers, because if there's no comma in between, the computer would read that as just one
Oh,
long,
like a whole number.
right.
Right, okay, so for their end, they have to make it. Yeah, I guess that makes sense.
It's from however their program is written.
Right.
And it's usually important that you put a key to clarify something like class value, place value.
Oh, please.
And so let's see how technically savvy I can be right now. I want to try to go back to our list of birthdays. And I don't want to copy all of this, but I do want to copy the list of dates. Yes, I did it.
Go, girl. Oh my God.
Okay. So I put it in the wrong place, but we did it.
Mhm.
Okay, so for the dates of birth, I'm going to do this twice. One's going to be my sloppy copy, and then one's going to be my final copy. My sloppy copy, some of those aren't 2-digit numbers. Some of them are only 1-digit number. So I'm going to put a 0 in the tens place. Then I can have all the ones with a 1 in the tens place, a 2 in the tens place, and a 3 in the tens place. And so over here, my stems are my tens places. Now for my leaves, I'm going to go through this list. The first number is a 13. So 13 would go in the tens. I'm going to just put the 3. And so I'm going to read that as 10 and 3, 13. Next number is a 16. That's in the tens place. I'll put the 6. And so I can see that as 10 and 6, 16. Then 20. I'll put a 0 because the ones digit is 0. Then the next is a 15. So in that row for tens, I'll put a 5. Then I have 7. 7 would be 0, 7. 4 would be 0, 4. Then we have another 13, so we need another 3. 17, we need a 7 in the tens. 29, so we'll put a 9 next to the 2. 28, we'll put an 8 in that row off of the 2. 21. Then we have a 16, so that'll go in that row with a 1 in the stem place. 6 would go next to the 0. 31, we put a 1 with the 30s, and then 21. And so that's my sloppy copy. What we need to do now is rewrite it in order. So for the next one, we're going to order them. And so again, it's the dates of birth. My stems are 0, 1, 2, 3. And if I put the leaves in orders, everybody all right? First would be the 4, then the 6, then the 7. When I order the next ones, what would I have? I'd have the 2 3s, the 5, the 2 6s, and the 7. When I put the 20s in order, I'd have 0, 1, 1, 8, 9, and 30s in order already. When I talk about putting a key, for the key, because these are birth dates, it makes sense that where I have, let's say, 1/3, it means the number 13. However, instead of birth dates, if these were something crazy like property values, 1/3 instead of being the number 13 might be a number like 13,000. Or for that matter, if these were like infection rates for the COVID virus, 1/3 might be something like the decimal 1.3. And it would be what, 1.3 positive per 100 tests or something like that. And so do you see how, depending on what your data is, that key is important to kind of tell you what it means. Have any of you seen a stem and leaf diagram before?
I feel like I've heard it, like the name of that, like in school somewhere before. I don't know though.
Can everybody wrap their mind around it and understand it? Would you work backwards? If I gave you this stem and leaf diagram, would you be able to say that our birthdays were on the 4th, the 6th, the 7th, the 13th, the 13th, the 15th, the 16th, the 16th, the 17th, and so on and so on?
Mhm.
It wasn't hard to make, was it?
No.
It gives us the same type of information as that group frequency distribution. We can see that there were 3 single digits. We can see that there were 6 between 10 and 19. We can see that there were 5 between 20 and 29. We can see that there's 1 in the 30s. But the advantage that this has over that group frequency distribution, do you notice that we didn't lose the single data value? So we know how many by looking, we can see how many are in each category. But we don't lose the data values. Sometimes when we look at a stem and leaf diagram, we see what's called a split stem leaf diagram. And we do that if we had a lot of values. If you have a large number of values, and instead of getting this number from the folks that are in class today, I was in a lecture hall and I had 100. If I had 100 people, some of those leaves might get pretty long, right? And so if I have a large group of large number of values, I might have 2 stems for each. And so I might have 2 zeros, and the first 0 would be for 0 through 4, and the second one would be 5 to 9. I might have 2 ones, and the first one would be 10 to 14, and the second one would be 15 to 19. And so we can split the stems so that it doesn't get quite as unwieldy, quite as long. And another thing you sometimes see is called a back-to-back stem and leaf diagram. That I might use to compare populations. And so I'm going to just make up data. I really try hard not to do this, but it's taking a long time to break the class. So I might, for an example, have something like test grades. And I might make a stem and leaf diagram with the stems in the middle. Let's say it's a good grade, it's 60s, 70s, 80s, 90s, and 100s. And I might want to compare the grades of the men in class to the grades of the women in class. And so I might put the leaves for the women on one side and I might put the leaves for the men on the other side. And you see how a back-to-back stem and leaf diagram would give me a way to compare the two instead of having 2 separate stem and leaf diagrams. Does that make sense?
So like for the men, it would be like 64, 62.
Right.
Okay.
Right. And do you see how this would be easy to make? would take a long list of numbers and make them organized. And in this way, it helps us kind of compare the two groups. Interesting?
Yeah.
Next one then that we're going to look at is something that's called a histogram. Has anybody ever heard of a histogram?
I have heard of that.
I know a million years ago when I used to teach at the secondary level, I taught high school math for years. Histograms and stem and leaf diagrams were once a part of the high school Regents curriculum. I don't know if they're still in there anymore or not. A histogram is a specific type of bar graph. When I look at a histogram, in order to be considered a histogram, the horizontal axis has to be the data values. When I look at a histogram, the vertical axis has to be the frequencies. The height of the bars has to represent the frequency of the data value. What's important with a histogram is that the bars must touch. Again, we want to label everything. To give meaning, so that whoever looks at our histogram knows what it's supposed to represent. And you need to put a break in the axis if you're not counting from 0. So I'm going to get cocky here and see if I can go back and copy our shoe sizes. And I'm going to try to make a histogram of our shoe sizes.
Excuse me.
Yeah?
Excuse you. Oh, that was terrible. Oh, I need to copy that. Oh, that's gross.
You don't have to recopy that list of numbers because it's going to show up in your histogram. So
Oh,
you
no,
don't-
I meant the notes. I was still copying the notes up top.
Oh, I'm sorry.
That's okay.
Let me know when you got it.
Was there anything under height bars represent frequency?
Bars much tough is the next
Okay,
one.
that's then, okay, then. leave all of it. Okay, thank you very much.
So our title is going to be the shoe sizes in class. Our horizontal axis has to be our data values. Our vertical axis has to be our frequency. In terms of that horizontal axis, our data values are our shoe sizes. So I would label that shoe size. that vertical axis has to be our frequency. If we wanted to, we just could call it frequency. But what is the frequency? Wouldn't it be the number of people? So I might instead label that as number of people. I apologize. My pen does not like me writing in the opposite direction. And so I guess it looks like Halloween writing, right? So is everybody familiar? Technically, when I draw a set of axes where they both intersect is 0. I'm a little lazy. I don't necessarily want to count up from 0. So when I say put a break in the axis, I mean, just put a little bit of slash mark in there. And that slash mark tells me, okay, all right, I know I'm counting up from 0, but I don't want to go 1, 2, 3, 4. So I'll start with my 5. Then I'll have 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm going to center each bar over the data value. And I should have, instead of copying the raw data, I should have copied our frequency distribution. I think I'm going to cheat a little bit and go back to our frequency distribution for just a second. The largest frequency that we had was 5. So my frequency distribution, my number of people, my frequency needs to go up to 5. So I'm going to try to make it evenly spaced here. And so we had one size 5. So above the 5, I want to have a bar with a height of 1. Because my bars have to touch, that bar is going to look like it goes from 4.5 to 5.5. But it's centered over 5. And it shows I had one size 5. Now, technically, we said the bars have to touch, but we didn't have any size 6s. So does it make sense because there was none there? It's going to look like there is no bar, but in our minds, we can picture that as a bar with a height of 0. We had 1 7. We had 1 8. We had 1 2 3 4 9 5 9s. We had 3 10s. We didn't have any 11s. We had 3 12s. 1 13 and 1 14. I have to apologize, in my list of things that must occur, I forgot to add that our bars should be of equal widths. So I guess we can add that off to the side, that the bars should have equal widths. And do you see how it's a graphic that shows what our frequency distribution shows? But we're just drawing it in a graph instead. What do you folks think of making a histogram? And if you were given this histogram, could you work backwards from the histogram and generate a list of data?
Yeah.
Yeah. Is it easier to look at the histogram and see what's going on than it is to just look at that list of numbers? It's a bar graph. The height has to tell me the frequency. The horizontal axis part of me has to be what my data is. I have to label it clearly, so if somebody didn't know what it was, they would, they could read it and see. And it's important that those bars touch. Again, the only time you might have a break is if there's the frequency of that data value is 0. Next time when we meet, we'll go and look and see what that histogram, how we would draw that histogram for grouped data. But I'm looking at the clock and we're just about out of time. So I'm going to stop sharing my screen and I'm going to stop recording.